Welcome back, everybody, for the final session of the day. It's my pleasure to welcome Erika Abraham. Erika did her PhD in Leiden and is interested in concurrency theory and formal verification, especially hybrid systems, and she has been the lead developer of one of the systems many of us have heard about, FlowStar. So now she's a professor at RWTH Aachen. So without further ado, welcome, Erika.
Thanks a lot for the introduction, and also welcome all of you. The last talk of today, so a bit further attention, and then you can enjoy the evening. I would like to do it a bit more interactive. So please, if I ask something, you do not need to just give the answer if you know or the idea that you have. Also, my talk is a bit different. I enjoyed the talks before. Tao talked about the part, approximative method. I will talk later. I heard about learning. I heard about abstraction, about timed systems or more complex systems, about SMP solving. All this stuff we are doing also to a certain part. But I decided not to use all my slots for the work we are doing, but give you some very basics, some nice things. I'm a theoretician. We do also practical things, but I love beauty in theory. So I picked a few topics from which I thought perhaps not all of you will know it, and it is worth showing some basic techniques that you can use in a lot of areas. But now on these examples, let us look what are really the basics, how a lot of methods work. So first I would like to talk today about timed automata. This is the most simple hybrid system you can imagine. So the only dynamics is time. But already this system is quite challenging from the model checking perspective. So how is the behavior? How can we analyze safety? I do not talk about liveness today. And then tomorrow I would like to make some decidability proof with you. So get some ideas. If something is decidable, how you can prove it. If it is undecidable, how you can prove. And there are some very nice tricks. So this is like in math. You can prove things, and sometimes you see, okay, it is proven, but it is missing something. It is not the direct way. And then it is sometimes wrong. But if you see it and you say this is beautiful, then it is usually also correct. So there are some nature ways that in the proof already the system, the main things are reflected. Like, so if you understand the proof, then you understand the system also better. So tomorrow I would like to give you some of these examples. And then on Wednesday I would like to talk a bit about what Tao talked about over-approximative methods for safety verification. So this one will be abstraction and by simulation are the main keywords. This is leading back unknown problems to known problems. And this is safe but inexact methods. That means we do not compute exactly, but still can provide some assurances about the results. So I do not consider cyber physical in that sense that I do not consider communication. I consider only hybrid in the sense we have discrete part. This is usually the controller, but can be also inherent in the system. Like, for example, a phase change by a material would be also a discrete change. But what is important, I do not talk about the type, but I assume a may semantics. What does it mean? If something can happen, it does not have to happen. So kind of non-determinism we have in the system. Sometimes there is a mass semantics. If a discrete controller step, for example, you say if a quantity reaches a threshold, then the controller takes some action, and then it has to happen there. What I tell you, we can extend to mass semantics, but I consider for the moment maze semantics. Okay, and the very simple example you probably already heard a lot of times in the thermostat, because it is very simple but still contain interesting aspects. So what is interesting, and this, not interesting, but the main components is that we have something dynamical. This is the temperature, which changes continuously over time. And this is a quantity whose value we cannot directly set. So this will not have these jumps as Tortoise showed us in the evolution, but it can change its dynamics. For example, by switching a heater on and off, and this on and off is discrete. So discrete does not mean that the domain is discrete. So we could have even a discrete variable with a real domain. That means discrete, by discrete variable, we mean that the changes happen at discrete time points, and it does not change continuously. There are different ways to model hybrid systems, and what I will consider is hybrid automata. So I assume most of you will know hybrid automata. They extend discrete automata, so we have some initial places, and there are discrete transitions between the places. We have variables. The transitions can be guarded, and they can change variable values. So they can have also resets, which I don't have here. These are the discrete transition systems, and we extend it by, during the control stays in a location or control modus, time evolves and the dynamic quantities evolve, and Tao also told us different equations. So there are different ways to model what happens over time. I will assume differential equations, and I will restrict up to linear in my 3 talks. That means the differential equation has the form, the derivative of a variable is equal a linear expression over the variables. And then we have also invariance in the locations. That means once you come in, the invariant must hold, and all the time you stay there, it must hold. Before it is violated, so at latest here, if x increases and reaches 23, then the control has to leave the location. Okay, so we have this mixed discrete continuous behavior, and this makes things complicated. Because historically, computer science grows from discrete, so programs, which can have, of course, real-time behavior, but the whole formal methods community was started in computer science with discrete systems, so model checking for programs, for example. But now it is mixed with the continuous one. And the continuous one comes, or perhaps the roots are more deep in engineering or in physics, where they have addressed a lot of important aspects like analyzing stability or also controller synthesis. But in this combination, this is quite challenging. And we still struggle with developing so efficient methods and tools that they are useful in practice. So what I address here is only the reachability problem, which is the basic safety problem. Is something bad reachable? And it means that we start in some initial states, and the system executes. We do forward analysis. You could also do backwards. And what we would like to know is whether the set of reachable states has a non-empty intersection with some bad states. So this is the problem I address in all 3 parts of my talk. And this problem is undecidable for hybrid automata. And it gets undecidable very early. I will talk about it tomorrow. But it is decidable for timed automata. So let us start with timed automata and look how it works. Who does not know how a timed automaton is defined? So all of you know the restrictions, right? The idea is we use these restrictions to define an abstraction. So who of you know how timed automata model checking works? Who knows such a picture already? Okay. Very good. So then perhaps you can help me later by the developments. This is a timed automaton. For the restrictions, I have also the definitions. So afterwards, if you want to look up the slides, you can read it. But I've always tried first on a picture, and then we get the definition, a short look, but then we continue. So what is important is we have as derivatives only one. So we have clocks, which measure the time. And all the conditions that we have compare clocks to constants. This can be strict or non-strict, less or larger, or even equality. But what we do not allow is to compare clocks to each other. Actually, if you have time, we will look tomorrow. I could use differences between clocks. This would still be decidable. So the difference between two clocks compared to constant. But if I combine it also with summing up clock values comparing to constant, we are already undecidable. So it comes very early. It is already a very powerful modeling language. And on the jumps, we can have resets, but we can only reset clocks to 0. The clocks are initially 0. And this last condition, we could even relax. So we could reset to a constant or start by a constant. It would be still decidable. But for simplicity, assume we start with constant and reset to constant. So you see it is quite simple. If we look at it as a grammar, we have what we call atomic clock constraints. They compare clocks to to constant. So x, y, z I always use for clocks and c for constant. So for example, x is less or equal to 2 would be an atomic clock constraint. And then I can build conjunctions of those. Only conjunctions. We have no negation, no disjunction. And of course, we can have some syntactic sugar, like a clock is from an interval and so on. Only these constraints I can use for reading variable values. So this is important for the decidability, that the only thing that I can observe is when certain transitions, the discrete jumps happen. So I can observe in which location and I am, basically, in which control modus I am. So by allowing only comparing clocks to constants, we only can see, if I observe what happens in a system, whether a clock value reaches an integer value. But I cannot see its exact value, okay? And because we are not comparing clocks, it is dimension-wise. And in the later we will see that this is what saves us, that we have decidability for the reachability problem. Okay, so reading, only comparing clocks to constant, and writing, only resetting to 0. This is the definition of a timed automaton for completeness. We do not need to go through it. So we have locations, variables, which are clocks. This is only for synchronization, not important now. And the edges go from one location to another. They have a condition, a guard, conjunction of atomic clock constraints, and a set of clocks which need to be reset. Okay? And we have invariants, which also clock constraints, telling how long I can stay in a location. And in the initial state, all clocks have value 0, but I can start in several locations. Okay, now let us give a semantics. Before we tell what is reachable, we need to know what is the semantics of timed automata. So we have variables, and the semantics is based on the values for the clocks. That means we need a function which we call valuation. It assigns to each clock a non-negative real value. Why non-negative? It always increases, derivative 1, and I can reset to 0. It cannot get negative, right? And we have a set of all valuations. So as you would expect, it is standard definition. A valuation satisfies, for example, x less than c if the value of x under this assignment is less than c. So straightforward, as you know it from arithmetic. Conjunction is true if both constraints that are conjuncted is true. And then somehow we will need to define what it means that time proceeds. And we have only clocks, so all clock values will increase with the same amount. That means if this is a valuation and t time proceeds, we will use this to denote the valuation where each clock value is increased by t. Okay? And the clock reset, if I go a jump, only a subset of the clocks will be reset. So this notation tells us that all clocks in this clock set R are set to 0 and all others are unmodified. Okay, now we are there that we can define the semantics and can come to the more interesting parts. So we have here an operational semantics. You know this notation? That means it is a basically a derivation system, right? I can derive passes of the system using these rules. I have no axioms. I have only two rules. Means if all conditions here hold, then I can derive this. So these are proof systems, deductive proof systems. Perhaps you know this notation. So when can I do a discrete jump? Is if there is an edge between two locations, L and L prime. This, you can forget about it, is for synchronization. This is the guard, and this is the set of clocks that should be reset. Now, what is the condition when is such a jump enabled is if the guard is satisfied by the valuation before the jump. The control is in the source location before the jump. Then I can take the transition to the target location. And what should hold after the step is I start from the valuation before. I reset the clocks that should be reset on this jump. And I reach a valuation which should satisfy the invariant in the location afterwards. Okay? So this is normal as also in the transition systems, nothing surprising. Additionally, we have a second rule which says time can proceed while we are in a location. And it can be if I start in a location L, by time I do not leave the location, I stay in the same location, and if t time passes by, then I just increase all clock values by t, and after that, the invariant should still hold. Okay, now I talked a lot. I said it should be interactive. My first question, I said that the invariant should hold all the time. All the time. They must not be violated. Now I require that I start in a state which satisfies the invariant. Okay, that I know. So before a jump it is satisfied, then it is satisfied after the jump. If it is satisfied before a time step, it is satisfied after the time step. How do I know that it is satisfied during the whole time step? Okay, so I know before, after it is satisfied. And I said the invariant must hold all the time. But I do not require it in this rule. Why not? Why? I said it holds all the time. But how can I show it? It holds before and after. And I know it holds all the time. There is a notion in math, and also Tao talked about all these representations are. Now we will get to the point why we allow only conjunctions of atomic clock constraints. What is an atomic clock constraint? X is less than 2, or convex. Convex. What does convex mean? Convex means if I have 2 points, they are in the set, then the linear combination is in the set. And linear combination, sorry, but I write also a bit behind your back. That means if we have 2 clocks, x and y, and I start in with a certain value, time passes by, both increase with derivative 1. That means it will go in this direction, right? Always. Okay? Now I start in a convex set, start here, let some time elapse, arrive here. This is a line. So if both points are in the convex set, then it cannot be that in the meantime they have left the set, because the set is convex. Per definition, it is always inside. So this is the reason why we do not allow these junctions, because then we cannot throw away the quantification. Okay, the first observation, only conjunction. And if we have this junction in the invariance, we can basically transform the automaton to a reachability equivalent one, but we get some problems. We'll see later. So it is not trivial how to handle non-convex invariance. OK. So when the state is reachable, if there is an initial state, and I apply only these rules, I move from one state. So the state is now, it's important to mention location and evaluation. And I move from one to the next, to the next, to the next. And the state is reachable if after a finite number of steps, I reach it by some path. OK? And the question is now, there are some tricks. What does it mean, reachable? And what does it mean? What do the passes of this automaton mean? Normally, we are used by defining an automaton, defining the semantics, and everything what you can derive by the semantics is a kind of valid execution, right? And there is this nice paradox of Achilles and the tortoise. This tells you the following. Achilles is very strong and very fast, and the tortoise is very smart. So they want to make a race. And the tortoise says, OK, let us talk about it first. Right? I can convince you that you have no chance to win. Because, well, Achilles, you are very fast, so give me a bit of a head at the beginning. So how much ahead do you want? And the tortoise says, yeah, 10 meters is sufficient. OK, Achilles says, yes, of course, 10 meters is nothing. I will catch you in no time. But the tortoise says, moment. You cannot catch me. Because, so what do you think, how long time do you need to do that 10 meters? So let's say it's a second or two. But the tortoise in that time already passed by, right? It also made a certain distance. It is less than 10 meters, but there's a certain distance. So once Achilles reaches the 10 meter, the tortoise is ahead, right? OK, then Achilles again needs some time to catch up that distance, but the tortoise moved on, right? And so it goes to infinity. Achilles can never overtake the tortoise, because when Achilles reaches the previous position of the tortoise has already again moved ahead. So what is now the paradox on this? Obviously, it will not happen in real time, right? What did we do wrong? That is the nature of paradox. It sounds logical, but there is somewhere a bug in it, something we did not consider in our definitions. What is it? What is wrong with it?
Well, the time step goes to 0 after time.
Goes means mathematically?
Continuous, I think.
Converges, yes. Exactly, it converges. Time converges to 0. That means, because now I argued in discrete steps, right? That means we have infinitely many discrete steps in finite time. And there is no processor doing this. It is not possible. It is not realizable. So infinitely many discrete steps in finite time is what we call synchronous. But if you think in time steps, there is nothing discrete in it. It is just that time proceeds and converges to 0 because it is slower and slower and slower and slower. So basically, you stop time. And this is what we mean by time convergence. So you have infinitely many time steps, but the sum converges to 0. And this is something we want to exclude from the semantics. It is in the semantics itself, in the rules, that they allow it. But then we make a trick. I do not talk about timed temporal logics. But in timed temporal logics, we say, OK, we do not consider all passes, only those which are time divergent. So we assume that somehow we can throw them out. And then there is a model checking procedure, which under some mild conditions indeed can do so. OK. So now we know what we want to analyze. And now let us go to how to analyze it. Now, what is the problem? Even discrete systems can be infinite state, right? How do we manage it? I mean, OK, programs, you said, I agree, large but finite state space is in practice infinite. But what is the trick? If you have an infinite state system, you want to analyze, for example, what is reachable. What do you do?
By simulation.
Exactly, and by simulation gives you an abstraction, right? So the idea is you have a concrete, we call it a concrete model. This is the big one. Even if it is not infinite, it might be big, so you want to make it smaller. You define a transformation. This is optimally based on a bisimulation. I will come to it what it is. Such that this is smaller, optimally finite, such that you can analyze it with existing procedures, and you get a result. And if you did this step fine, then from this result, you can give some conclusion for the original system, for the concrete one. And if you did it good, it's even equivalent, if this is a bisimulation-based transformation. So what does it mean in our case? We have a timed automaton. It has an infinite state space, uncountably infinite, hopeless. Okay? You cannot check all possible passes. Because even if you do it infinitely long, you will not catch any or possible passes. So we transform it to something discrete and finite. And today we talk only about reachability, so I have a finite automaton. I can check what is reachable, right? This is easy. And then the result, from this reachability result, I can compute the reachability result for the timed automaton. Okay. And this is conservative, safe abstraction. And now you said already bisimulation. So what do we mean by bisimulation? What is bisimulation? How could you define it? Bisimulation based on simulation. What could simulation mean? Even if you are not from that area. If I simulate, what do I do?
Observe some behavior.
Yes, behavior is a very good word. But something is given. Okay? If I simulate a system, the system is given. What should I do that I call my behavior simulation of that behavior? What is important?
Model of a system.
I'm a model of a system, right? But what does it mean? When do I model it good? Can you tell me any requirement? So for example, we heard about learning a model. When could I say my model is good enough?
By testing.
Okay, testing. And what do I do by testing? Yeah, I give input, right? I give input and I see the output. That's all I can see. We have seen I cannot see the state of the system, right? I can make experiments with it. I can tell him something and I can look what comes out. And depending on what is this notion, what we call observation, what I can observe, and we call about the observable semantics of the system. If I hide some part of the traces of the passes, but certain properties of it I can still see. Okay, and simulation means that I can do so as if I would be that system. Okay? So if I can give the system something and it gives an output, I can do the same. So I would like this one to be a bisimulation of this one. That means if this timed automaton, I want to now know reachability. Assume we simplify the whole thing. I want to know whether a location is reachable, not to go to logics, temporal logics and this stuff. Whether a location is reachable. So if I see this one, a location is reachable by going over a sequence of locations, then this should do the same, and vice versa. Okay? So they, of course, have different behaviors, because this is an abstraction. But it has not thrown away anything. It can still do the same things. If something is reachable here, it will also be reachable here, and not more. Exactly the same observable. So now two things need to be fixed. I asked Short, when do I have to finish?
5 to 10 minutes.
Okay. So important things we have clarified to know what to do. Now let us look how we do it. So now we have this infinite state space. How can we abstract it? And by simulation, we already said what it is. It means I have two systems, or even one system has two different states. And if I start from them, and that what I can observe by letting the system run is the same, then I call them bisimilar. That means if from one I can go to the next location, then I can do it also from the other one. So you can imagine if I have a partition of the state space, which typically, let's say this is our state space, and I can divide it into, by an equivalence relation, into subsets. What does bisimulation mean? If I have two states in the same equivalence class, then if I can go from here to the next one, and I can only see when I change the class. Okay? Inside, what happens inside is not visible. Visible is the boundary, so if I can go from here to there, then I can do it also from this. Then they are bisimilar if it holds for all. So from here, again, if I can go to here, then I can also from here. So the passes on the boundaries, between the boundaries, are the same for all states in each class. It would be over-approximative if some would miss, okay? Because, now I don't have another color, but once I have this abstraction, whether it's by simulation or not, doesn't matter. Oh, that is excellent, thank you. What I do is I take the classes as abstract states. So I look at this as it would be one state in the abstraction. And now, based on this state space abstraction, I define a transition system. So where do I go from this? If I want to if it is a bisimulation, then I go to the next class when there exists a transition between any states. Okay? So if there is a transition from this state to this state, then I go from this abstract state there. And I go from this abstract state there. But now you see, if it is a bisimulation, then this passes, I can go from all states here. If not, it might be an over-approximative, because now from here I cannot, if this is missing. So it's over-approximative. If I can prove that the abstraction is safe, the original will be safe. But now if this is missing, if I can prove that the abstraction is unsafe, I cannot say anything from the original system, because perhaps it is this way. And there is no counterexample in the concrete model. So bisimulation is very nice because the two things fall together. Over and under approximation fall together to an exact representation. And this is a very, very nice property, and this is what we would like to have. So how to abstract the state space? Now I have this whole, assume two clocks, okay? It is easier to imagine we have two clocks, and the two clocks, now I have the next problem. Here, I take this one. So we have two clocks, and the question is, or two states, when are these two states bisimilar? And let us do it by looking at when they are not bisimilar. So let me take, so the clocks are non-negative. This is the value 1, value 2. Okay, now it is not so exact, but this is, okay. So if two states have not the same location component, of course they are not bisimilar, right? Because the thing that I can observe is the location. I can observe directly that they are not the same. Can you tell me now two states here that means x, y value pairs, which are not bisimilar. Because in a timed automaton, they have the same location component, perhaps. But in a timed automaton, I can make one step, and it makes a difference. So from one state, I can do a step to some location, and from the other, I cannot. They are not bisimilar. They cannot bisimulate each other. Can you tell me two values? I help you a bit. Perhaps here I have a location, and I have a jump. Here I have a condition x equals 1. Tell me one state from which I can go this transition and one state from which I cannot.
So 0, 0,
Mm-hmm.
and 0, 2. That's the one that cannot.
OK, but from 1 I want. So let's say 0, 1, OK?
Yeah, 0, 1.
Perfect. They're not equivalent, right? Why not? Because there is an atomic clock constraint. One is satisfies the other one not. OK? So basically, this line, for example, separates. Everything on the left of the line is x less than 1. On the line is x equal 1. Right is x larger than 1. So they cannot be equivalent, right? They already have 3 classes. But that I can do for each clock. So I have here these lines, which distinguish about the integer values. And here these for the next clock. And the combination. So basically, this line segment is different from the rest. This point here is different. So all line segments and all points cannot be equivalent, right? These line segments are still OK. And inside, we have to look. But basically, I have to distinguish. So we know that equivalent states should satisfy the same clock constraints. That means they are both have the same integer value, and they are on the lines if and only if. But it is still not OK, because I can do it for 2, for 3, for 5, for 4, 5, 6. And then at the end, I have infinitely many classes. So I can still not model check. That's a problem. But there is a solution, namely, in my model. Then it is not a bisimulation anymore in general, but there is a given timed automaton I want to model check. And in this automaton, there is a largest constant. For example, x is compared to 3, but not to a larger constant. That means if x gets above 3, then all states are equivalent in the sense that either all can go transitions or none of them. OK? So it is sufficient to test only after the largest constant. So if it is 2, then here I stop. So I have a kind of partial grid, like this. And each line segment, each point at the grid is different. And now we can ask the question, is it a bisimulation? And it is not yet. And this is a problem because it blows up a bit things. So here you can see intuitively, if I have these 2 points and I let time elapse, then from this point I will reach first the condition y equals 1. And from this I will reach first x equals 2. So for example, if I have here an invariant y is less or equal 1, then from this state, first the invariants get violated before this guard gets enabled. That means from this state here, I have to go here this way. And I cannot take this transition. Whereas from here, I can do both, because first x equals 2, and I can still stay here till y equals 1, so I can go both. It is a difference in behavior. And this can be solved by adding these diagonal divisions between the state sets, because they express that the fractional part of the clocks, there's an order on them. Here they equal, here the fractional part of y is larger and here the fractional part of x is larger. That means they will get first to the next integer value where something can happen. And now this is a bisimulation. That means this, for example, this point represents this set. And this set inside is bisimilar. That means I can just plug them together to an abstract state. But you see, there are quite a lot. So instead of this, there are some more modern taxes. This is difference-bound matrices to represent not only single sets, but sets of such so-called regions. Just one more thing we need to do. We abstracted the state space. What is missing? I mean, we have now abstract states, but what do I model check? So what did we do? We had a timed automaton. It had a state space. We abstracted the state space, and now I know in the timed automaton, if there are two states in the same set, then from that I will visit the same location sequences in the timed automaton. But I do not want to model check the timed automaton, but something finite and discrete. So I need, with this state set, now I have to build up an automaton, a discrete one. Okay? And this is quite easy, but still there is one or two tricky things. So we need to connect transitions. I will leave the slides for look up, and just in a minute I explain you the only tricky thing. So if I have this abstraction of the state space, I want to add transitions between them, okay? So let me do a very simple abstraction. Here we have, of course, the clocks. And I have here, I can say only as long as y is less or equal 1. And here, I can go if x equals 1, and this is my target location. Okay, so let us call this L, let us call this L prime. So if I build the state space abstraction, now I have, fortunately, not so many discrete states, abstract states. Namely, I have this one, this one, this one. And with not so many, I mean, Naya. There are still quite some, but OK. So the breakpoints represent my abstract states. Which transitions do I add? When I start here, both are 0. This is this abstract state, OK? Now I take green one for the abstract transitions. I start here. Which one do I reach from this? Where should I add transitions between the states? Well, let us look. Here I start with both are 0. They increase, and I can stay here as long as y is less or equal 1. So from here, I can move to here, and then and full stop, because the invariant is violated. Okay, so for that, we can define something like successor relation means I add a time step between two states. If in the automaton, I can let time proceed, and I get from this set to this set without visiting any other. And this without visiting any other is very important, because if I would add also things here, for example, jumps here, I would jump over this, right? But perhaps from here, I get somewhere else, and only from here, because the transition guard is here, that's x is between 0 and 1. Then only from there I can go. So if I jump over, so here, on every path I have the possibility to go. Here, on this path, I would not. So I must not jump over visible events. That's why I just take the direct time successors without jumping over any others. This is the first important thing. The second one is, now let me take away this condition here. Then I can stay longer. OK? But now let me pose one question, and this is the last important question for this abstraction. actually, if I'm here, I can do several time steps. Okay, so here I could add the self loop. No, here not, because that is just one time point. And here also, because I can stay there. I can do a time step and stay there. And I tell you, this one I need, I must, and this one is a must not. Why is it that if I add this loop, then I do something bad? Can you tell me a property, location sequences, a sequence of visited locations? Time progress. Okay, time progress. If I edit here, I edit time convergent behavior. So there exists a path on which x never gets 1. Okay? But of course, here only by time convergent passes, which are not realistic. So I need to exclude them. I only want reachability via time divergent passes. And if I add this one, I lost. If I remove it, I can still reach the same things, but inside an abstract class, it is not visible anymore. However, here I need to add it because otherwise I get deadlock, right? Otherwise, once in the abstraction I get here, I cannot move on. But of course, if once time passes beyond every bounds, it can still pass on. So there is no what we call time lock. So I need to add this loop, but it is okay. It models time convergent passes, but there are also time divergence ones. I know for sure. Once I'm here, every pass can diverge in time. Okay, and that is the magic. So now we have an abstraction. Here is an example. So for example, if here I can do this jump always if x, which is initial 0, is at least 2, and then I reset x to 0. Now I added a second variable, z, which starts also at 0, and I can move here if it is at most 2 and x is 0. So the abstraction only in L is I start at 0, go here, 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 and I can stay, and if x is at least 2, I reset x. So now I have also jumps. I can move from here, where x is 2, to x is 0. So these are transitions here. Let us look how it looks in the abstraction. I start here, which is number 1. Then I move to 2, to 3, to 4, to 5, to 6. And for example, from 5, I can reset to 0. Then I get here to 7 by a discrete jump. And from 6, if I reset to 0, then I get to 12. And from those, I can again continue. And now I have here something. It is very nice because it is finite. It might be big, but it's finite. And then I can model check it. For reachability, it's very easy. I just check forward reachability. For temporal logic, it's a bit more complicated, but you can do it. And then, because it was based on a bisimulation, I check whether in the abstraction I can reach a location, and the answer holds also for my timed automaton at the beginning. So this is the nice thing about bisimulation. But sometimes, as you see, you need to consider a lot of small things, a lot of details. And if you understand what is a bisimulation in a timed automaton, then you learned what is the nature of a timed automaton. Why does it work? And then you know why were those conditions put that, for example, you need convex invariance, that you compare only clocks to constants, because then you can do this abstraction. If you compare clocks to each other, then you are lost. And then you can see what stops working in a bisimulation, and then you understand what people thought by putting up this definition. Okay? Very good. This was for today. And tomorrow, we will do some proofs to show that you can extend a bit this syntax and remain decidable. But very, very, very fast, we get to undecidability. And the main challenge there is to prove undecidability. We have things that evolve over time. If you want discrete programs from which we know undecidability resides, you, for example, add up 1 to a variable. But now, another variable is unchanged. You cannot stop them here. A clock always evolves. So can we simulate, by dynamics, discrete behavior? Sounds easy. It is not. I'll show you tomorrow why. Thank you.
Thank you very much, Erika. Questions?
I can imagine that you are all tired after listening all day to a lot of different topics. But I hope that something remains, and some ideas, some inspiration from all the talks. You hear a lot of new topics, new expressions, new ways of handling things. But this lot of impression. After some weeks you are at home, I think then it will start working in your head. So if you have any questions, I'm happy to answer.
I have a couple of quick questions, if that's okay. So the abstractions here are, we map to the points. Do we have any kind of region in the original system that we consider to be corresponding to this? Or we just take these single points?
This is a single point different from all other in behavior, in general, so you cannot. But of course you have a certain system, and in this system it might be that it is equivalent to others, depending on which conditions you have.
But in general, there's no kind of region that's connected to it somehow.
No, exactly.
Yeah. So another quick question is, do we have, when we talk about the sets, do they need to be open or closed for the conditions, for example?
Here it indeed does not matter, so you can also have open conditions. However, with open conditions you must be a bit careful, because this is exact. Okay, so you can handle also open ones. But once you, for example, change a bit the semantics, you introduce must transitions, which need to be taken when they are enabled. And that moment when they get enabled, what happens if you have an open? X is larger than 1, which is the first time point where it gets enabled. So in this setting, we are safe. If you move a bit over, approximative methods, of course, cannot handle non-strict things. So here, it is everything nice. If you move a bit out,
then you have to be a little bit more
yes,
careful.
have to be careful what you do.
Yeah, very good. Excellent. Thank you.
In this example, why do you have the loop as 2-2 and not at 1-1?
Because here, if I would add 1, then I could stay here forever. But that means the clocks would stop running.
Yeah.
Okay, this is actually a single valuation where both clocks have the value 1.
Okay, because in the transition you can transition at x equals 1. Yeah.
Yes, but so here there is no path, no time divergent path that would start by 0, 0, then something between 0, 1, 1, 1, 1, 1, 1, 1, 1, 1. There's no path in here. If I add it here, then I add a path which is not in here. So for example, if I analyze a property, it is always eventually x larger than 1. Here, true. Here it would not be. So you see very small details where I can lose by similarity. So I mean lose this property of the abstraction that it is if and only if. But here I have to add, otherwise there would be no infinite path. There was another question.
Okay. Assuming that we need to add, we need to model the communication also in this model, are we going to add additional states in our timed automata, or are we going to add some invariants in the state
for communication, you mean?
Model the communication
so
between the
in this in this area, communication is not considered as a, let's say, first-class citizen. That means we do not have communication channels and this stuff. Communication you can still model by adding labels here.
Okay.
And communication itself, it is also a beautiful area because you can have so many different ways to model communication. So label synchronization is one of the easiest communications things. It says that if you want to communicate a value from a finite domain, you can always encode it as a bit vector, okay? And then you communicate always by synchronizing a label, and this label, for example, here I write A, and A means by me,
So it's in probability.
for example, something, right? So if I take a transition here with A, then in the parallel composition, the other one also needs to take a transition with A if it has A, if it synchronizes on A.
Okay.
So this way I model that they do something together, that they exchange information. Another kind of communication is shared variable communication, right, in programs. This is also one. Then you have synchronous, asynchronous. Here we do usually only synchronous communication, but of course you can have also asynchronous. Then you have the lossy channel thing. So if you go in that area, it gets an own area on its own, independently of what kind of models you have for the actual behavior. So we usually take just label synchronization, and right, at least we have compositionality thereby, but also very interesting and relevant.
And just to check, I guess we can model delay here in communication. So if I send something, maybe we can model that it takes some time.
Yes, but again, it is not a first class
Yeah.
modeling component. You can model it by clocks
Yeah.
and by conditions, yes.
Yeah.
But if you would model it first class, then you would add a kind of transition.
Primitives or yeah.
Yeah, such that you can also make use in the analysis or what you do afterwards, that it is a certain type of weighting. It is not just a clock reaching a value, but it is a channel, I don't know,
With some properties.
expiring or whatever.
Mm. Very good. Any other questions? So we're ready for tomorrow's continuation. Thank you very much, Erika.
Thank you.